Lesson 4-4, Wave Properties. Energy can be transferred in two basic ways. One way is by physical contact, when you actually apply a force by touching an object over a distance. Since force times distance is equal to work, anytime work is done, energy is transferred, so that's one way to transfer energy is by physical contact. Energy can also be transferred by waves, and sound, light, ocean waves are all examples of energy transfer where the source of energy does not directly contact the receiver. And of course there are two types of waves, but with mechanical waves, instead of direct contact, the energy is transferred through a medium. And a medium, just like in the room that you're in, if there were no air in the room, you wouldn't be able to hear me, because the sound waves are transferred from the speaker in your headphone or from the speaker on your computer to the air, and the air transfers the sound waves to your eardrum, and you hear that. If there weren't any air, there wouldn't be a medium, there wouldn't be a transfer. So a medium is any material that the waves can pass through. It is only temporarily affected by the wave energy and returns to an equilibrium state after the wave energy has passed through. So here's an example of a pulse, and that pulse is traveling along a wave, and of course it disrupts the medium for a brief period, but once the wave has passed through, or the pulse has passed through, the medium returns back to equilibrium. So the medium is pushed up as the pulse moves to the right, but returns to the initial state of rest after the pulse moves on. So that's what's happening to the air as I speak. Instead of being pushed out of equilibrium in terms of a physical of a wave, we see in air, we see the pressure change. And so as the wave passes through the air changes pressure, and of course that pressure is then transferred to your eardrum, which vibrates, and you pick up that oscillation, and your brain interprets it as some kind of sound. So we can look at a wave and see what some of the properties are from this simple little diagram. So from the wave train above, we can identify and define some important wave properties. These are properties that you should know a little bit about. Of course, the dotted line represents the equilibrium position, where the medium would be at rest. Now you can think of, if you've ever jumped into a pool at a motel or a hotel, and you're the first person in that pool. You've been in it for hours and it's smooth as glass. Well, the water in that pool is at the equilibrium position. There aren't any waves in that. And of course, as soon as you jump in, what you do is you push the waves out of equilibrium. Some of them go up and some of them go down. When they go up, we call that a wave crest. So number 2 here, these represent wave crests. Here's another wave crest over here. With water waves, we say a crest is above the equilibrium position, and then of course below the equilibrium position we have something called a trough. On some waves the troughs and crests are identical, and so these three troughs would be identical to the crests, except for instead of being above the equilibrium position, they're below. So they are no different than a crest, except the energy displaces the medium in the opposite direction. So we have a crest and we have a trough. Now the amplitude is basically the distance from the equilibrium position to the top of a crest or to the bottom of a trough. It's the maximum displacement from equilibrium, and our last definition is the wavelength. So from the top of one crest to the top of the next crest, that would be considered a wavelength, or from a trough to the next trough, that would be exactly one wavelength. Or from this point right here to the identical point on the wave, the next identical point on the wave, since the wave is going up at this point and it's going up at this point, then that distance 5 here would also be a wavelength. But most of the time we say it's between one crest and another. So this is the typical 5, but you could also be between a trough and a trough, or between any two identical points on a wave. All right, so those are some important concepts and ideas that we need to understand when we're talking about waves and wave properties. So when a smooth pool of water is disturbed, the energy of the disturbance moves out in something we call a wave front. It's a circular group of waves. The circular wave front moves away from the source. And of course, this is a single wave. If we get a whole bunch of waves moving at the same time, let's say you lined up 50 pennies along a board and then dropped all of those pennies into the water at the same time. Each penny would produce a set of wave fronts, circular wave fronts that look something like this. But a whole bunch together, something like this. And of course, the circular wave fronts merge into what we call a parallel wave front. So the wave front looks something like this. And that's why we see waves coming in fronts rather than always being circular. What happens is each circular wave front interferes with the adjacent waves. From side to side they sort of cancel out, but going away from the source they interfere positively with each other and make this this front right here. And of course it goes in both directions from the source. And so each circular wave front interferes with the adjacent wave, and the result is waves like those on the ocean or on a wave pool. So this is called a wave front. Since we understand a little bit about what a wave front is, if you took the opposite track and said, okay, let's look at some wave fronts that we have, or a wave front that we have, and reverse the process so that the parallel wave front then hits a barrier or a gap. What we'll find is that if this wave front were to hit these two bricks that are placed in its path, what will happen as that comes through will be a circular wave. As this wave comes through in this direction, it will produce a circular wave front when it goes through the boundary. Now this is something called diffraction. All right, it's called wave diffraction. It was first explained by Christian Huygens, and Huygens' principle says that any part of a wave front acts as the source of a new wave. Any part of a wave front acts as the source of a new wave. What does this mean? Well, what this means is, of course, that since diffraction is a property of waves, Newton's and Huygens debated whether light was a wave. One of the things that Young used was the evidence of diffraction. Since Huygens explained that diffraction could only be a wave property, he was able to show in 1805 that light showed diffraction properties, and therefore light must be a wave. One of the things that Newton had argued was that light was some kind of particle. All right, so here's what happened. What Young did was he took parallel wave fronts like these, and he shot them at a barrier, just as we did in the previous example. And he found that they would produce a circular wave front in this direction. He then extended that and said, instead of just wave fronts through a single slit, he passed them through a double slit. And of course, a parallel wave front moving through a single slit produces circular waves, as explained by Huygens' principles. A parallel wave moving through a double slit produces a pattern of constructive and destructive interference lines. This is something that works with water waves, but it also works with any other kind of object that is wave-like. And of course, even light produces these interference patterns. And this is explained. These destructive and constructive interference patterns are caused or are explained by the principle of superposition. What you can see here is that from the top wave, or the top slit and the bottom slit, you're getting areas where you have wave crests. All right, the lines represent wave crests. Between the lines you have wave troughs. when a crest meets a crest, something interesting happens. So all these points of intersection are when crests are meeting crests. And what happens when a crest meets a crest? What happens when a trough meets a trough? Well, let's take a look. So when a crest meets a crest or a trough meets a trough, this is explained by using the principle of superposition. So when wave crests and troughs from different sources interact, the energies of each part add as vectors to replace the medium or displace the medium from equilibrium. If the displacements both have the same direction, you will have something called constructive interference. So in this case, what you have is a wave crest meeting a wave crest from another source. What's going to happen when? Well, a crest meets a crest, and of course what you get is something called an antinode. All right, an antinode is an area of maximum constructive interference. So we call this an antinode or a maximum, and of course it's an area of maximum deflection from equilibrium. Notice this wave goes up a certain amount, this wave goes up a certain amount. The resultant when those two meet is that they deflect the medium even further from equilibrium, just for a short period, and then of course they continue on their way. They don't bounce off each other, they pass right through the medium and pass right through each other. They don't affect each other, they only affect the medium. And so the medium returns to equilibrium, and the crests continue unaffected by the interaction with each other. All right, so they affect the medium, but they don't affect each other. This is known as interference. So what happens when a crest meets a trough? So if a crest meets a trough, then we get something called destructive interference. So here we have a crest on the top of the wave, it's moving to the right, and a trough is on the bottom of the wave and it's moving to the left. So in this case, a crest is going to meet a trough, and of course when they do that in the middle, you will get a momentary cancellation. All right, a momentary cancellation where the positive deflection of the first crest is canceled by the negative deflection of the medium by the trough, and you get this momentary cancellation. It doesn't quite look as flat as we've drawn it, but that's called a minimum, and another name for a minimum is a node. So maximum is called minimum is called node. And of course, as these two vibrations or disturbances pass through each other, remember that they don't affect each other, they only affect the medium. And so the medium, again, after a while, it remains unaffected, but of course this wave crest continues towards the right, and the wave trough down here continues towards the left. And so the crest and the trough continue unaffected by the interaction they just went through. When they produce a node like this, the medium is flat for just a moment, but then you get the waves continue on, and the medium remains unaffected. So we have antinodes, which are produced by constructive interference, and nodes, which are produced by destructive interference.